You remember so it was having this product form, and actually your the orbital part of G1 and G2, they are same, like phi 1 into alpha and phi 1 into beta and so on. So actually n by 2 orbitals and n number of spin orbitals. And these G's are just, say, self-consistent Hartree orbitals. We have already discussed how we can generate the self through iterative techniques. And the main problem here is, although it can take care of electron repulsion in some approximate way, it has a serious problem that it violates Pauli's antisymmetry principle. So if you interchange the levels of any two, it would generate a totally new one. But we know that for fermions like electrons, in fact, if you have a binary permutation operation interchanging the levels of two electrons, the wave function must change its sign. Okay, so that means it would be the same function multiplied by -1. Okay, but it is not happening over here. So you have to take care of this, and that was done by Fock. So we have to now go for Hartree-Fock theory. So what is the improvement on the Hartree-Fock theory? Actually, as you can see, it is mostly Hartree theory, but you have something additional in order to just take care of the Pauli's exclusion principle. So this is your, Hartree theory, they introduced a kind of Coulomb operator that takes care of Coulomb repulsion between the electrons. Okay. So in the Hartree-Fock theory, you have a Coulomb operator, say if I call J, this is your Coulomb operator, and you have one exchange operator. I will tell you what exactly do we mean by exchange later. So this is exchange operator, something like Kj. Okay. So this Coulomb operator, let's say for a given stuff, we are calculating, say, Jj1 and Kj1. Jj1 will tell that it actually measures the Coulomb interaction between electron 1 and a smeared out charge density rho j as phi j mod square. Okay, this is actually coming from Hartree theory that we have already seen. Okay. This one takes care of the Pauli actually antisymmetry principle. In a special case, you can see also the exclusion principle. So this is your exchange operator. This is Coulomb operator. Remember, in the last class I told you about the integral. That means you have to take care of two such and integrate over the space. But this is an operator. There is a difference. So if you calculate the integral, you will get a number. But here this operator, you have to operate on a function. Okay, so we will see what is this Coulomb operator and what is this exchange operator. Perfect. So here in the Hartree-Fock theory, actually what happens, say, it starts from a set of, let's say, xi1 1, xi2 2, xn. These are your, say, spin orbitals, and you can start with the hydrogenic spin orbitals. As in case of Hartree theory also, we started with originally the hydrogenic orbitals, then we improved upon it by incorporating somehow the average way electron-electron repulsion. Here, this one would be like your phi 1, 1 into alpha, then phi 1, 2 into beta, and so on. So ultimately it goes up to phi n by 2 into beta, okay, of the nth electron. So that is the way you can start with, and these phi's are your hydrogenic orbitals like 1s, 2s, 2p, etc. Now you get, let's say, F11 phi 1 as E1. I can, in fact, you can see, I can put Xi1 also, there is no trouble in a general sense. Why? Because Xi1 is your phi 1 into alpha. I have phi 1 into alpha, because this operator depends only on spatial variables. There is no spin dependent operator over here. So that is constant, alpha or beta, that is constant. So I can take it outside. Here also I can take it outside. Anyway, this is multiplicative, and I can cancel them. So whether I write in terms of phi or xi, this spin orbital, it doesn't matter. You understand? So because it doesn't have any spin dependence. So whatever we are doing, this type of calculation we call non-relativistic calculation. So in quantum mechanics, you will hear this term, non-relativistic calculation, means we are not taking care of the spin. Spin we are putting it by hand. If you have to take care of the spin, you have to go for the relativistic quantum mechanics. Like there you have to solve relativistic quantum mechanics. So there you have to solve Dirac equation, let's say, Dirac equation. But we are not going to do it now. We are doing only the non-relativistic calculation. We don't want to get spin information per se. Okay. In that case, the operator will have to contain both space and spin dependent operators. In non-relativistic calculation also, separately we take care of spin orbit interaction or scalar relativistic corrections, etc. So suppose if you have to tackle heavy elements, okay, you have to lanthanides, actinides, there you have to take care because their relativistic effect is non-negligible. Okay. So if you do the calculation, you know at least little bit you can get through say Los Alamos type LAN L2 DZ or TZ type basis, where some kind of scalar relativistic stuff will be there, but otherwise proper spin orbit interaction, etc. should be there.
How crucial it is to run heavy elements under relativistic calculations?
What?
Like how crucial it is in the absence of Deb's calculation? What makes
You see, the correlation is roughly 1%, but for heavy elements, relativistic correction is almost 10%. So if you are doing even a totally uncorrelated theory like Hartree-Fock theory, and you are doing relativistic correction, you will get a better result than you are doing very sophisticated like CCSDT type calculation without any relativistic effect. For lighter elements, correlation is important because the relativistic effect is not that important. Okay. Actually, crudely I can tell you, have you ever heard of this like Russell-Saunders coupling and JJ coupling? You know, the Russell-Saunders coupling is valid for lighter elements, where spin orbit interaction comes as a perturbation. First you have electron-electron interaction that is much stronger. Okay. So that all L vectors get coupled, all S vectors, and then ultimately L and S there would be some weak coupling to give you J vector. That is your spin orbit coupling. On the other hand, if you go for heavier elements, you have to go for JJ coupling. So at the very first instant, you have to couple L and S for individual electrons to get individual J's. Okay. So that you have to see the relativistic effect where you can neglect and where you cannot neglect. Okay. For heavier elements, obviously you cannot neglect them. But as I told, that proper relativistic correction, say you have to solve Dirac equation, but there you, instead of wave function, you will get 4 component spinors, etc. That's a very difficult algebra also. But within non-relativistic framework, you can add it by, say, adding some spin orbit interaction, etc., as perturbation and so on. Or through basis set also little bit scalar relativistic you can get. Okay. Here, this equation, actually as you can see that this is for 1, as you remember in Hartree theory also we did for electron 1, then we focused on electron 2. Here also you do it for 1, 2, etc., effectively up to n by 2. Okay. These equations, the set of equations, they are called Hartree-Fock equations. Okay, so these are your Hartree-Fock equations. And once you solve these equations, you will get the final, let's say, Z1, 2, up to n, let's say with tilde. That means the final SCF solutions. But instead of a product wave function, in Hartree-Fock theory, you get like 1 by n factorial to the power half, and then this one is a determinant. So this is your psi Hartree-Fock 1, 2, n. So what it says that your determinantal wave function, so this is your Hartree-Fock wave function, which comes in the form of a Slater determinant, as opposed to a product function which was there in Hartree theory. So this is determinantal wave function plus variational principle. They imply your Hartree-Fock equations. So whatever Hartree-Fock equations you can see over here, if you take this as your trial function, where they are hydrogenic orbitals, let's say, and then you construct the energy functional, do the variational say calculation, the equations you will be solving at the end, they are your Hartree-Fock equations. Okay. So now this one we will call Fock operator. So in Hartree theory, the corresponding operator along with your electron-electron repulsion part, the Coulomb operator, I can call that as the Hartree operator, let's say. If you add now the exchange part, it will become Fock operator. So let's see what type of operator is the Fock operator. Okay. Actually, I am doing it over the orbitals. The 2 factor is coming because there are 2 electrons in each orbital. and this is your Coulomb operator, this is exchange operator. So when it operates, let's see, and what is your H01? This is your core Hamiltonian. We already seen this is the same core Hamiltonian. That means it is your minus half del 1 square, this for electron 1, minus Z by R1. And for molecule, it should be minus sum over alpha Z alpha by R alpha 1. Okay. So that would be a difference. In case of molecule, it would be simply like this. Okay. This for atom, many electron atom. So you can see, you can solve Hartree-Fock theory for both atoms and molecules. So this is your core Hamiltonian. What is the effect of this operator? Let's say JJ1 operating on phi A1, it would be integral phi j star 2 phi j2 by R1 to d tau j, and this is operating on phi A1. Okay. So you can see that this plus this up to this, it is your Hartree Hamiltonian, isn't it? So this is the same thing which Hartree has used, or the way we wrote it there, integral phi j mod square by R. So this would be R1j, R1j d tau j. This operator operating on phi A1, and this is of course phi A2 star if I call, and then I can call it R12 and this over 2. Actually, if I write phi j, then I can write it jth electron d tau j and R1j, and then 1, 2, 1, 3, 1, 4, everywhere I will get the similar terms. Okay, so that we have seen. So one with each, that would be done. So that one was simpler. What about the exchange part? Now there is a crucial problem. Say Kj1 phi A1, it would be integral phi j star 2 if I call jth electron, actually I am telling it 2, that would be easier, phi j star 2 phi A2 by R12 d tau j, okay, or R1j, let's say. So d tau j, and this would operate on phi j1. So here you can see your solution comes inside the operator. And here instead, your starting solution is coming, it is operating on the starting solution. So you have to take care of this operator, and this is an integral operator, okay. But you can see that this is actually it was operating on phi A, but phi A is coming in the operator itself, and there is exchange of this phi A and phi j. That's why this exchange operator. And this would be there for all j's. Like your phi a, the solution you want, should get exchanged with all phi 1, phi 2, phi 3, except phi a, all of them, it should get exchanged. So, what is the basic difference between, let's say, Hartree equation and Hartree-Fock equation? That firstly, Hartree equation, you can just calculate the integral and put it there, exchange, and then you did the spherical, the approximation, etc. But that operator is there, okay, like this type of operator is there. But this operator, in principle, this is an integral operator there also, there also. So these equations are one electron equations, but they are integral differential equations. They are not simple differential equations. You have differential operator coming from H naught, and also you have integral operator coming from this Coulomb exchange, Coulomb operation or the exchange operation. There is additional problem that to solve this now you have to know the solution beforehand. So these are called non-linear equations. So your Schrodinger equation is a linear equation. Okay, but these are non-linear equations. What are the non-linear equations? You have to know the solution to solve the problem. How can you do it? So you come across non-linear solutions in many places. I will tell you, if time permits, how to solve the nonlinear solution so that you get some idea how you solve these equations, Hartree-Fock equations. So you have seen the Hartree-Fock equations. You iteratively now you have to solve for individual electron, focusing on individual electrons. But only thing you have to remember that you have to know the solutions to construct the operator to solve the equation. So how do you do this? Apparently it's a paradoxical that you are solving something, but beforehand you have to know the solution. How do you do it? So that we'll tell in a moment, but before that, so do you understand what is the basic difference in Hartree theory and Hartree-Fock theory? Only thing, you have added the exchange operator, and exchange operator, the job is that it wants to see what happens if you just exchange your orbital on which you are focusing with all other orbitals. If you exchange all of them, what type of difference will you get? And that is precisely your binary permutation, what you are doing in order to check your Pauli's antisymmetry principle. Okay? So then we will see how you can do it. Now we will see how generally we solve. We generally don't solve per se the integral differential equations. As I told you, we convert it to a matrix. And this idea was this is mainly by Ruthan. So it is called Ruthan-Hartree-Fock theory. Okay. And that is the way in computer we solve the Hartree-Fock equations. So let me write it like this: fj1 phi j1 okay. So this is your, and we know what is Fock operator. So what he did, he had chosen some basis functions, let's say chi alpha, and then you write each phi j. In fact, let's say I don't assign any electron index at this moment. So phi j is sum over alpha C alpha j chi alpha. Okay. That means I am taking the linear combination to initially construct phi j. Instead of putting hydrogenic orbital per se, I am constructing hydrogenic orbitals or whatever in terms of some basis functions. And that we have learnt enough, how to express any arbitrary function in terms of the linear combination of the basis functions. So if I just substitute it over here, what do I get? See your, let's say fj, I am writing this like this: fj operator operating on this one, sum over alpha C alpha j chi alpha. This is Ej sum over alpha C alpha j chi alpha. Okay. And now we have already learned the technique how to solve this. You pre-multiply by chi beta star and integrate, let's say, over d tau j. Okay, you do these two operations: pre-multiply by chi b star and integrate over d tau j. So if you do this, what do you get? Sum over alpha C alpha j integral chi beta star f j chi alpha d tau j okay. But what is this one? This is your chi beta f operator chi alpha. This is your chi beta chi alpha. Okay. So this one, we know this, we call, this is now a number f beta alpha. That's the matrix element, beta alpha matrix element of Fock operator. Okay, that means if you construct the Fock matrix, it would be betath row, alphath column, that element. Okay. This one is your overlap matrix, S beta alpha. Okay. Perfect. Do you have any confusion? Tell me before we proceed further. What I have done, I have left multiplied by chi beta star, then integrating over the electronic coordinates of the jth electron. Okay. Okay. These are anyway, these are numbers F beta alpha, C alpha j, this is Ej, okay. But can you tell what is this? This is the matrix element, beta alpha matrix element of F operator. This is alpha j matrix element of C matrix. What is this quantity? Any one of you, what is that quantity? What? What? But don't tell anything. If you don't know, tell I don't know. You see, suppose if you have two matrices, A and B, product is, let's say, C. You know, these two matrices should be conformable for multiplication if the number of columns of this would be same as number of rows of this. That means if it is m by n and this is n by p, this is you can multiply them and the final matrix should be of the dimension m by p. Do you know this? How do you do this multiplication? Suppose if I want to get C ij, ijth element of C matrix, how do you get? Ith row of A multiplied by jth column of B, and then sum over all of them. That means Cij is your sum over k A ik B kj, isn't it? Do you follow? That is the way you are doing. Look here. A beta alpha, C alpha j. So if you take the product of F and C, it is beta jth element of that product. Okay. And similar equations you will get for all such j's. That means this side, if you have F matrix into C matrix, this side you have S matrix into C matrix, and E also, all of them I can put it along the diagonal that we have seen, and if I call this as the E matrix, I get FC as SCE. This is the matrix equation. We have already learned how to create matrix equations and how to solve them also, that we have learned. Okay, you can see that FC equal to SC is the matrix equation in which we have converted my original Hartree-Fock equation in terms of a basis set to the matrix equation. Okay. I haven't done any extra mathematics. It is just simple product of two matrices. Okay. These equations, so this is set of equations. You know the matrix equation basically set of n linear simultaneous equations. In this case they may be connected because they are nonlinear. So they are called Ruthan equations. Ruthan-Hartree-Fock equations or simply Ruthan equations. So actually when we solve Hartree-Fock equation for, let's say, any molecule or any polyelectronic atom, we solve Ruthan equations. Okay? In a given basis set of your choice, you expand that chi you can choose, and then the matrix you have to construct, and the matrix equation would be solved the way we have learned how to solve the. So first you have to construct this matrix, and that also you have learned. Matrix representation of an operator, like here the Fock operator, what is the matrix representation in the given basis set chi, and then the corresponding matrix, we have to solve the matrix, these eigenvalue equations, and that is your Ruthan equations which you can solve. Okay? These are a little bit difficult, but if you read, it is not at all difficult. The thing is, you have been solving this on a regular basis. You must know what is going on at the background. Okay? And don't leave it anyway, we are getting numbers, we are getting papers. Okay? You will be a stupid, intelligent person. You are getting numbers, people will tell, okay, he is doing great research, getting publications. But if you ask any question out of it, you won't be able to answer. Okay? So it should be your first job to learn what is there inside. Whether you are getting garbage out of it or not, that also you must be able to tell. Okay? In fact, analytically, that's why one 2 by 2 matrix we have solved, isn't it? And how to construct the corresponding matrix, that also we have learned. So this is the typical mathematics is known, and here only this is the application, that the Fock operator in a given basis set chi alpha, we have expanded it, and then we got the final form as the Ruthan equations. Okay? If you have any question, please tell me right now. What's the time? 10:45. 10:40. 41. Okay. So maybe I will tell one extra piece, then afterwards we'll talk. So now, how to solve non-linear equations? Okay. And first of all, let me tell you what would be your non-linear equations and how to solve them. I will take a very simple example of a non-linear equation. Okay. So how to solve a non-linear equation. Let's say if I have ax square plus bx plus e to the power log of sin x, this is equal to 0. Or I will make it a little bit more complicated, e to the power sin of log x. You can see this is a very complicated equation, isn't it? And it is highly nonlinear. Now suppose if this would have been a constant, then even a school kid could have solved it, isn't it? What is the solution? If it is a constant c, let's say, what is the solution? This is a quadratic equation. Ax square plus bx plus c equal to 0. X is what? If you cannot tell, get out of this place. What is, if you have an equation ax square plus bx plus c equal to 0, what is x? Yes, minus b plus of minus square root b square minus 4ac by 2a. Good. So you could have solved it very easily. Now let's see whether we can do the same trick over here or not. Okay? So I have some time. Maybe I can teach you a little bit of numerical analysis also. You remember how we are solving those equations? Go back to Hartree. You start with hydrogenic orbitals. That means some trial stuff, hydrogenic orbitals. Do this operation once, get another set of better quality orbitals. Then you construct the operator, Hartree operator, again you go back, get another set of even better orbitals. Do it until you get cell consistency or the result which is according to your expectation. Okay, that's the way you have done. Here, suppose if I identify this as my C, then I know the formula. Just now we told, but we don't know C. But suppose if I take this X, I can immediately get this one. A specific value of X can give you a number. Perfect. So then I put it there, solve the equation. After solving the equation, now I get another X. I put that X in that expression for C. Do you follow? Again solve using that formula. Sridharacharya formula that is called. So you solve it, another X you get. You keep on doing it until two successive such iterations, X will be very close to each other. Technically you can tell that they are same, they are not changing. That is your solution. It's a very, very complicated equation, non-linear equation. This is the strength of iterative solutions. Do all of you follow how we are doing? Yes or no? Tell how. Be louder. Can you hear anything? Be louder. What? You are jumping the steps. Say, first you take a specific value of X, calculate the value of C. You have X square plus Bx plus C where C is a number. Get the X through the solution of that quadratic equation using the formula what you just described. With this new value, you again calculate C. Again, you solve the quadratic equation. Do it until two successive iterations you get the same X or two X's within your tolerance limit. Perfect? So you see how generally, so in the Hartree equation, actually we are doing exactly the same thing. Isn't it? Or Hartree-Fock theory, we are doing basically the same thing. Okay. I can tell you there are several such, say, numerical techniques. I don't know, did you attend any numerical analysis course? Any time, anywhere before? If you want to write computer programs, you must know numerical analysis. No. So this is something which very famous, say, Newton-Raphson method. Do you know what is Newton-Raphson method? No. Never ever heard of it. You do the Google search and learn. So if I call this whole stuff as a function of x, so your fx equal to 0 is your equation. You write x n plus 1 is x n minus fx by f prime x. Okay. So find out what is your fx. You take the first derivative like 2ax plus b plus whatever is the derivative of this. You put it over here. Now you take any arbitrary value of x. So calculate fx value f prime x, this x, that will give you new x. You go back, you do it again, the same thing. Keep on doing it until your xn and xn plus 1 will be within a reasonable tolerance, like xn plus 1 minus xn by n plus 1. Okay, to do it iteratively, you will get a solution to this equation. That's called Newton-Raphson. It's somewhat better than what I told. So this is, you must search it in the Google and learn what is Newton-Raphson technique. Okay. So these are the techniques what you must learn numerically. Otherwise, it would be difficult for you to solve any problem, mathematical problem or physical problem. Maybe after this break I will tell you what type of requirement is there in order to learn completely whatever you are doing. Okay? Okay. Now actually I would like to tell you something about the way we formulate the problems and we solve the problems, so that you can understand, say, it's not necessarily what we do is the right approach, but that is the approach which is being followed. So first I will tell you about the reductionist approach. Now, what exactly is the reductionist approach? It is assumed at the very beginning, like your social problem is the superset. You can follow all social problems, their solutions, etc., as if that's a handicap of, say, it's a handicap of the human civilization. So how the human minds they work, and then the biological functions. So you reduce a social problem to a biological problem. Now after that, so this is what is called reductionist approach. You reduce. All biological problems can be translated to chemical problems. So whatever happening inside any biological body is due to some chemical reaction. So if you can follow the chemical reaction properly, you can understand the biological problem. Now what about the chemical problems? So in a chemical reaction, what would be the speed of the reaction, whether the reaction will at all go or not, etc., etc. At the end of the day, it turns out to be a physics problem or a physical problem. So whole of chemistry can be explained in terms of physics. Physics cannot give you any solution, because physics, let's say, will give you certain equations, Newton's equation, Lagrange's equation, this, that, but you have to solve. In order to solve that, you have to learn mathematics. So at the end of the day, you are reducing everything to a mathematical problem. The thing is, you have to learn how your problem moves from one domain to the other. Okay, suppose if I tell you physical or let's say chemical problem. This is often complex. As I told you previously, even a biological problem can be converted to this problem. Okay, so physical or chemical problem, that is at our disposal. I am seeing a particular reaction. It may go, it may not go, it may take 200 years, it may take 2 seconds. Now, this is the problem, what is at my disposal. Or I am throwing something, whether it is going or not. Okay, some projectile. I am moving someone, but it is not moving. So these are physical and chemical problems, but sometimes they are very, very complex. So what I do, I go for certain models. Model means, see, you have classical mechanics, you have quantum mechanics, you have statistical mechanics, you have molecular mechanics, and so on. So you apply any one of those mechanical stuff. So depending on this one, I will call length scale and time scale. If they are very large in dimension, my classical mechanics will be there. If they are very small, similarly, if it is a very fast process, if it is a very slow process, you have to choose accordingly which particular mechanics will fit, and you construct the corresponding model. That means now I have some equation. Okay, that means this physical or chemical problem with this model I have converted to a mathematical problem. Now this mathematical problem means I have some equation. It may be linear equation, it may be differential equation, it may be integral differential equation, integral equation, or maybe even a very, very complicated other type of equation, transcendental equation, any type of equation. So that is my mathematical problem. So I have reduced my physical problem to a mathematical problem. Now these mathematical problems, sometimes they are solvable, like you have a particle in a box problem, you can analytically solve, hydrogen atom you can solve, harmonic oscillator you can solve, rigid rotor you can solve, but they are all ideal systems. Actual oscillators are not harmonic, they are anharmonic. But if it is anharmonic, analytically you cannot solve. If you go even for helium atom, analytically you cannot solve. So you have to find out whether they are solvable or not. So you have this equation, your computer doesn't know, you have to instruct how to solve. If you give the equation, there is no instruction. So for that you have to convert this, you have to go for what is called numerical analysis. So I have given a very little hint of Newton-Raphson technique. For all possible such stuff, you have a numerical technique. If you know the numerical technique, then your mathematical problem is converted to a programmable problem. Like if you ask a computer, what would be the sum of 2 and 3, let's say two numbers, computer will not be able to tell. You have to instruct how to add 2 and 3. Okay, that means you have to write a program. Computer doesn't know your mathematics. So then it becomes a programmable problem, for which the problem is such that now I can go ahead and write a computer program so that my computer can understand. Okay. Now if you have a programmable problem, say you have to have like flow chart, you have to write flow chart step by step how people will do, or in other words I will tell depending on algorithm I will write, the step by step instruction I will give, this is called a high level language. High level language means which we understand, that is high level language. But computer doesn't understand high level language. Like Fortran, Python, C++, Java, Pascal, Basic, these are all high level languages. So this we know, we can learn, and we can write a program using that language. Now this is the software portion of the computation. Now it goes to the hardware portion. That means once you have this, you get a computer program. Okay, so first you write step by step numerically how you will have to do, and then you take help of any high level language, write a computer program. So it may be your Fortran program or Python program, C++ program, that is here, program. But computer, so there is a component called compiler. So compiler, the job is to convert high level language to machine language. That would be like several zeros and ones, etc. That again you won't be able to understand. Computer will be able to understand. So compiler job is to convert your high level language to machine language. And then it will solve your problem and you get the results. Then your job would be again to analyze the result. This is also equally important step. Getting result, that's not the end of the story. You have to learn how to analyze a set of results. So you can see these are various steps what we need to follow. We need to follow, I am telling you. But what most of you are doing, you jump from, okay, and here you don't know who has written, how it was written, nothing you know. You would be told blindly, you press that button, press this button, write this one, maybe 10 different commands would be able to solve, but background you may have 1 lakh statement program, and that was written by a group of people maybe over a period of 25-30 years. Okay. But the major problem is even if you get the results from the program, then if you want to calculate something else, you have to write at least small computer modules. If you don't know how to write those programs also, and if you don't get that output from your program, you will never be able to explore something whatever you have in your mind about the physical or chemical problem. Okay? Like if I ask you to find out the pKa of some acid and see your Gaussian output is not there. But you know what is pKa, but you don't know how to calculate pKa. So it will be a handicap for you. Okay, you will not be able to do anything whatever you like. Okay. So at every stage you can see your knowledge is required. You have to know physics, you have to know chemistry, you have to know these mechanics, you have to know the mathematics, you have to know the numerical analysis, you have to know which one is programmable, you have to learn some high level language, you have to learn how to write a program, you have to learn how to solve that program, and then get the results, analyze the results. All the steps you have to learn. Okay? Okay, now if you see the exact non-relativistic energy minus your Hartree-Fock energy, you get what we call correlation energy. Okay, so we have learned two different terms, correlation and exchange. So if you get a theory which is beyond Hartree-Fock theory, which includes correlation, they are called correlated theories or post-Hartree-Fock theories. Okay? Post-Hartree-Fock theories. So there are several. This is called configuration interaction, multi-configuration self-consistent field, coupled cluster with singles and doubles and triples for the energy calculation. Then you have molar placet series MP2, MP3, MP4, etc. You have DFT. So there are several. So these are all post-Hartree-Fock theories. All of them, some amount of correlation is there in all of them. Some are highly correlated, some are little bit correlated, but they are all post-Hartree-Fock theories. Okay. So configuration interaction, how do you get it? Suppose if I write 1s2, that means 1s into alpha for helium atom as your phi 1, 1s into beta as your phi 2, and then you write psi 1 2 as 1 by root 2 factorial. This is your Hartree-Fock theory, remember. So here you have phi 1 1, phi 1 2, phi 2 1, phi 2 2. Now this determinant, this is a ground state determinant. Let me call this as my D0, determinant 0. Now suppose, now I take another, so these are called configurations, you know, electronic configuration. Suppose if I have this configuration now. So here you have 1s into alpha and 2s into beta. Okay, or 2s into alpha also, that would be another. So these are different like D1, D2, D3, etc. Okay. So these are various configurations. Now they are interacting, that's why it's called configuration interaction process. So your psi of Ci would be sum over I Ci di. Now I am taking linear combination of all those. So here these determinants are constructed in terms of SCF orbitals, both occupied as well as virtual. As you can see, 2s is a virtual orbital. Okay, you construct all possible such determinants. Okay, so they are what? So one electron is going from 1s to 2s, means this is electronically excited state. So not only the ground state, we are combining the configuration for the electronically excited states also. So once I have this, which one would be the best? That also I have learnt it, the variational principle. So I construct, let's say, E of, let's say, this one if I call xi of Ci, then this should be the typical Hamiltonian, electronic Hamiltonian. And now I will again construct del E del Ci equal to 0. The determinants are fixed. They are obtained from, let's say, the Hartree-Fock solution, all Hartree-Fock orbitals, both occupied orbitals and unoccupied or the virtual orbitals. We construct all possible configurations, all possible determinants, take their linear combination, variationally optimize the linear combination coefficients. I will get the configuration interaction wave functions. If you go a little bit further, suppose if I tell no, that SCF orbitals, they may not be that good to consider the correlative effect. So apart from these CIs, I will optimize these DIs also. DIs means, let's say I have written the original Hartree-Fock molecular orbital in terms of certain basis function. The corresponding linear combination coefficients of that also we can optimize. That means you get additional sets of such first order derivative to be 0 or corresponding linear equation. Instead of n number of unknowns, you have 2n number of unknowns and 2n number of equations. Okay. So that will give you MCSCF, multi-configuration cell consistent field. So basic differences, in one case only the coefficients, in other case coefficients as well as the determinants, they are optimized variationally. Couple cluster, you get some cluster operator, expand it, the Hartree-Fock one, you do the single excitation, double excitation, etc., and then you construct, basically again you do it this way. DFT I will tell you a little bit more. MP2 is basically a perturbative technique. You consider your unperturbed solution as the Hartree-Fock solution, and then you, or little bit the first order perturbation also, and then you add, keep on adding the second order correction, etc. In standard perturbation theory, you know how to calculate the corresponding first order, second order perturbation corrections. So these are all your post Hartree-Fock theories. If you do this, your energy will go very close to the exact non-relativistic energy, which is way better than your Hartree-Fock energy. So Hartree-Fock energy, you see the step-by-step development, your original hydrogenic system, very, very crude. Then you have the Hartree theory where electron-electron repulsion is taken care of, but Pauli exclusion principle is not there, Pauli antisymmetry principle. Then you go to Hartree-Fock theory where both Pauli antisymmetry as well as electron-electron repulsion is there, but correlation is not there. In order to incorporate correlation, you have to bring in the, say, interaction between all possible configurations. Okay. So you go for post Hartree-Fock theories where the energy would be very close to the exact non-relativistic energy. So now I will tell you, at least in the simplest possible way, how we can understand exchange air correlation. Okay. Sometimes the exchange is called Fermi correlation, and correlation, simple correlation is called Coulomb correlation. Okay, exchange basically is a Fermi correlation, and which takes care of your Pauli's antisymmetry principle. Why Fermi correlation? Because it is the larger requirement is that they should obey Fermi-Dirac statistics. So Pauli antisymmetry principle is just the outcome of the obeying of the Fermi-Dirac statistics. Okay. So this is the statistical requirement, and that's why we call it Fermi correlation. Now what exactly it is? We are still within orbital picture. Okay. That means if we want to do now, why do we need this exchange correlation or Coulomb correlation? When we get the orbitals, we are putting one electron in each orbital. Okay, even in Hartree-Fock orbital, one electron in one orbital. Now, the electrons are moving. They are not static. So there is a possibility, let's say the two electrons come very close to each other. When they come very close to each other, what happens? First of all, each orbital, you see, we did not take spin into consideration. Each orbital is defined in terms of three quantum numbers, let's say n, l and ml. I am telling crudely for atoms, three quantum numbers. Now suppose two electrons are having the same spin. They come very close to each other. They come very close to each other means their orbitals are becoming same. So they will have already three quantum numbers same, and they are having the same spin. That means it will violate Pauli's exclusion principle. But that will violate everything of quantum mechanics. That will violate Fermi-Dirac statistics. That is the problem, because you have a many particle problem. If you would have taken correlation properly, they will not be allowed to come very close to each other. But now you didn't do anything. So that is the problem. You have to add exchange, which was done by Fogg in the Hartree-Fock theory. In Hartree's theory, that restriction was not there. So what happens now? It is assumed that each electron, when it moves, it carries with it some excluded volume. Like snails, they have something which they carry. Okay, for let's say turtles or tortoises, they have some, say, hard cover so that no one can enter into their place. So each electron is carrying some excluded volume around itself. Okay, it's like this. This is some excluded volume. So no one can come within this. And this is what is called Fermi hole. Okay, or sometimes this is called exchange hole also. Exchange hole or Fermi hole. It is moving, but always not allowing someone. But if you want to put it, let's say, inside your Hamiltonian or the corresponding operator, how will you do it? It is assumed as if some fictitious imaginary force, repulsive force, is acting between two electrons of the same spin when they come very close to each other, so that they cannot come and hit one another. That repulsive force is, this force is called exchange force or exchange, and the corresponding energy is called exchange energy. You will talk about exchange correlation functional, these, that, etc. You have to learn what exactly we do physically we mean by exchange. Do all of you understand what is exchange now? So exchange, you can see that it is for the same spin. If they are of different spin, obviously that restriction is not there. Okay. So you get what is called Fermi hole. Now we think about something else. The electrons, there are two properties. Apart from spin, they have charge also. Now when you bring the two same charge species, when they come close to each other, they will feel infinite repulsion. And if they hit one after the other, one above the other, then it will reach what is called a singularity. That's called Coulomb singularity. Because it will face infinite potential. Because you know the potential is what? 1 by r. R is the distance between the two particles. If it becomes 0, it becomes infinite. Okay. So repulsive potential becomes infinite, means it has reached what is called Coulomb singularity. And that is again because of your orbital picture. If it would have been wave function, in the many particle wave function, it wouldn't have caused that trouble. Your picture is single particle picture through which, because still we are talking about orbitals, Hartree-Fock orbitals. So here what will happen? Again the same thing will happen. So apart from the Fermi hole, it is also carrying another hole, another excluded volume with it because of the charge. But now all electrons, because charge of all electrons are same, -1. So any electron coming very close to other electron, they cannot come very close to each other. That means you have to consider that it is carrying another hole called Coulomb hole now. In addition to Fermi hole, you have this hole, this one I will call Coulomb hole. Again, exactly in the same fashion, we can consider that the electrons, because of the same charge, they will face some additional, it is not your original Coulomb repulsion, that is there in Hartree theory, but it is because of your orbital picture, you have to add something else. You have to force them not to come very close to each other, and you add some additional fictitious force. That is what we call correlation force, or simply correlation, or the corresponding energy is called correlation energy. So now you can see, you have learned exchange correlation, you have written it several times here, there, you have written in DFT calculation, exchange correlation functional, this, that, etc., B3 leap functional, etc. How do they calculate? They simply model this repulsion, exchange repulsion. Let's say first it was shown, the simplest one is the Dirac exchange, Slater exchange. Then you today you use Becquet exchange, Pardue one. Now various types of ways of, because these are all fictitious, so you can develop your own theory to get a functional for this. Why functional, that I will tell you maybe in the next class or next to next class. So you get exchange into correlation, different types of functionals are available now. And what is exchange, what is correlation? If you don't know properly, obviously you will learn how to type that name, but without understanding what is Becquet functional, what is leap functional, if you don't know, you are doing some clerk's job, not a scientist's job or researcher's job. Okay, so you have to learn. So here today, at least qualitatively, I explained you what is exchange, what is correlation, where exchange comes in Hartree-Fock theory, but it was not there in Hartree theory. In order to get the correlation, you have to go to the post-Hartree-Fock theories like DFT, CCSDT, MP2, etc., or CI, MCSCF, all those theories. Okay, so next class maybe we will start from density. Okay, so these are all wave function based pictures we have told so far. Okay, so stop at this point. You cannot bring them close to each other. They are correlated. They are correlated in the sense that correlation will not allow them to come very close to each other. Okay, this is the repulsive hole. will not allow them to come very close to you. Hmm?
The coalition might probably stop the electrons from moving. Only when the electrons stick to some places, then there is a
So
transition.
you can come, but after starting this.
Until
Not
within the week.
So you have some hard cell, and that's the hard cell. You cannot take it. Okay. Cannot happen. I'm telling you, suppose if you have H2 molecule. H2 molecule, you can see. So not only hydrogen molecule is covalent totally, it may have some, let's say 1% ionic character also. But suppose there are molecules like lithium fluoride.